The next thing that we're going to discuss is actually not a new thing to you. We actually use many of this in Calculus 3. That is determinant of a matrix. So for example, we call, in Cal 2, we know that if you have a matrix A, B, C, D, 2 by 2 matrix, then the determinant is AD minus BC. Okay? But in this section, we're going to discuss how determinant of an n by n matrix is defined. But you probably know that, but let me make a remark anyway. Determinant only makes sense for, so only defined for so-called square matrix, or aka n by n matrix, okay? So the number of rows equals to the number of columns. So let us have a look on how it's defined. The definition actually comes from a mathematician, a very important mathematician called Laplace. Laplace says that, or define determinant of matrix by, okay, what's the idea? The idea is he take the first row, okay, the first row, and then he adds sign, so plus, minus, and so on, okay? Then how does he define the determinant? The determinant is defined by, firstly, I have A11, so this A11, and then plus big A11. What do you mean by big A11? Big A11 is the determinant of the matrix obtained by removing the ith row and jth column. For example, big A11 means you remove the first row and first column. Whatever you have left here, you compute a determinant. And then what's the next term? The next term is a minus A12, because A12 comes from a minus, and then big A12. So you remove the first row and the second column. Whatever you're left there, compute the determinant, and then so on. And then in literature, this way to define determinant is called Laplace expansion. But actually, the name is not very important. Here, I want to make a remark about the notation of a determinant. So notation. There are two commonly used notation to write determinant. The first one is literally write it as that, okay, determinant of A. And other one is to write it as A and then with two lines next to it. It looks like absolute value, but it has nothing to do with absolute value. So these are two very common notation to write down determinant of a matrix. So you should know both of them. This kind of thing, if you look at the definition, it looks crazy. But let us go through a concrete example very carefully, and it will make a lot more sense. So this example. Find the determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so what's the determinant? So what we're going to do is to take the first row, so first row, and then when I get plus, minus, plus. So I know that the determinant is 1 times something, and then minus 2 times something, and plus 3 times something. Okay, but what do I multiply to? So 1 is here, is the 1, 1 entry. What we're going to do is to remove the first row and first column. Whatever you're left there, so I have 5, 6, 8, 9, and compute the determinant, okay? And then moving on. 2, okay, 2, the sign is a minus, so minus 2. And the 2 is 1, 2 entry. So what we're going to do is we remove the first row and the second column. So what do I have left? 4, 6, 7, 9. So the determinant of 4, 6, 7, 9. Okay? And then finally, I have 3. Okay, 3. And 3 belongs to the 1, 3 entry. And then what we're going to do is to remove the first row, third column. Whatever I have left, I compute the determinant 4, 5, 7, 8. Okay, And then now we compute them. Because 2 by 12 determinant, I know how to do it, is AD minus BC. So 45 minus 48 and minus 2 times 36 minus 42. And plus 3 times 32 minus 35. So this minus 3 and then plus 12 and then minus 9. So at the end, the answer is 0. Okay? So that's it. But actually, I know a priori that the determinant of this matrix is 0. Because, spoiler alert, okay? Why do we talk about determinant here? So, spoiler. Because the determinant of a matrix equals 0, that is equivalent to the rows being linearly dependent. Because this is a very famous rows, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. From week 1, we know that these 3 rows are linearly dependent, okay? They have linear relation between them. And therefore, from what we will see on the next page, that can immediately imply the determinant equals 0. The underlying principle why this is true is because, okay, determinant can also be computed using Gaussian elimination. And that is what we're going to discuss on the next page. Okay?